Hello, we're going to talk about section 4.1 part 3 today, the last part of section 4.1. Here's an example. The height of a ball thrown upward from a point s sub 0 feet above the ground. S sub 0 is the initial height. Anything with a sub 0 is the initial, and then s is our height. With an initial velocity, so v sub 0 is our initial velocity, that means the force with which it is thrown upward from wherever it was. Feet per second is given by what function? So we're going to start with our acceleration. If you remember, if you start with your position function and you take the derivative of it, what's the first derivative of the position function? Another name for it is the velocity. If you take the derivative of the velocity function, that will be your acceleration. Well, since we now know how to do antiderivatives, if you start with your acceleration and you do the antiderivative, that is how you can get a velocity equation. So let's start with our acceleration and take the antiderivative of it with respect to the variable time. The antiderivative of negative 32 would be negative 32t plus a constant c. So our velocity function is negative 32t plus a constant c. We don't know what that constant is right now. Let's think about the units. We started with negative 32 feet per second squared. As you integrate, the units change similar to how they changed when you were taking the derivative. So for example, if we had feet for our initial position and you take the derivative, it becomes feet per second. So derivative is almost like dividing by time. And then the derivative, again, would be feet per second squared. As you do the antiderivative, we start with feet per second squared, and it's almost like we're multiplying by time, by seconds. So the units on this would be feet per second. To get from our velocity to our position function, because we're trying to find the height, which is our initial position, or our position function. So to get from velocity to a position function, we want to integrate the velocity. So we're going to integrate negative 32t plus c with respect to time again. And remember, when you're integrating, you can integrate each piece separately, and that's just a constant. And when you're integrating with a constant, you can pull a constant out. So we could pull that constant out and just integrate the number 1, or that seems kind of silly, we might as well just integrate the constant. But here, we're going to have negative 32 times the antiderivative of t. That exponent there is 1, so we're going to add 1 to the exponent, divide by the new exponent, plus a different constant. We'll call that c sub 2. And then plus this constant here times the antiderivative of 1, which is just the variable t, and then plus its own new constant. Well, this...
Mr. Kapsner, if you're still in the building, please dial extension 1601. Mr. Kapsner, extension 1601. Thank you.
Sorry about that. So c sub 2 and c sub 3 were the constants we added based on integrating from velocity to position. So two constants added together would just be one constant. So instead of writing it twice, we're just going to write that one constant here. And let me simplify a little bit. So our position function is negative 32t squared over 2 would be negative 16t squared. Putting that in standard form, we want this next, and then finally that. Well, does that look familiar? This is where we usually put our initial velocity, and this is where we usually put our initial position. So that's where that equation came from, the position function. It starts with our acceleration due to gravity, and then you just keep integrating and integrating. So the height of a ball thrown upward from a point s sub 0 feet above the ground with an initial velocity of v sub 0 feet per second is given by this function, negative 16t squared plus v sub 0 t plus s sub 0. how high will a ball go if thrown upward from the ground with an initial velocity of 50 feet per second? So now let's start from the basic. We're going to do the antiderivative of the acceleration to get our velocity. So the antiderivative of negative 32. So this is a particular example of the previous formula that we came up with. Doing the antiderivative of negative 32 with respect to t is negative 32t plus c. That's our velocity, but we know this is thrown upward with an initial velocity of negative 50 feet per second. So if the initial velocity is 50, what was the time when its velocity was 50? Initial means that the time was 0. So at time equals 0, the velocity was 50 feet per second. So v of 0 is 50. So that means since this is our velocity equation, I mean to put 0 here, we can put 0 in for t and find our initial velocity. But we know our initial velocity is 50, so we can find c. When t is 0, our velocity will be 50. So we can solve this for c. Negative 32 times 0 is 0. Subtract 0, we get c equals 50. So our velocity equation is negative 32t plus 50. Since they give us the information, we have to use it to find the particular solution for velocity. Then we're going to integrate that to find our position function. Because we're trying to find how high will a ball go, we need to know its position function. So we're going to integrate the velocity with respect to t. And I'm just going to do this all in one step instead of writing separate integrals. So negative 32 times the integral of t would be t squared over 2. And I can do plus c now or just at the end, so I'm just going to do it at the end. Plus, and then the integral of 50 with respect to t is 50t plus c. That's my position function, and I know this ball was thrown upward from the ground, so at t equals 0, what was my initial position? What was the ball's initial position? It was 0, it was on the ground, it had no height. So s of 0, which is our equation negative 16, just simplifying this here, t squared plus 50t plus c at 0, whoops, I should have put 0 in, sorry, 16 0 squared plus 50 times 0 plus c. When time was 0, this position was at 0. This ball's position was 0. So simplifying this, we get c equals 0. So that's going to go there. So our final position function is negative 16t squared plus 50t plus 0. So you don't have to write that. So that's the official position function for this particular example. And we want to know how high the ball will go if thrown upward from the ground with an initial velocity of 50. So think about a ball, it's getting thrown up, and then it comes back down. We want that maximum point. So we want the maximum of this. Think about your steps of finding the maximum of something. To maximize this, we want to take its derivative. Well, we already have that. That's right here. So take your derivative, set it equal to 0. Oops. Negative 32t plus 50 set equal to 0 is going to be negative 32t equals negative 50. Solve that. We get negative 50 over negative 32. .5625. So at time about 1.5 seconds, this ball will reach its maximum. I want the position, how high. I didn't ask when will the ball reach its maximum or when will the ball be at its highest point. If the question said that, then I would answer at 1.5625 seconds. But I want to know how high. So I plug in that 1.5625 into the position function. Remember to read the question carefully to see what it's asking. Often they will ask when will it reach its maximum? And sometimes they'll ask, how high will it be when it reaches its maximum? So that position will be about 39.063, rounding. If you truncate, it's 39.062. So that would be feet. Those are the units. All right, let's say we have a balloon, rising vertically with a velocity of 16 feet per second. That balloon is like a hot air balloon. From that hot air balloon that's rising upwards, a sandbag, we release the sandbag and it drops to the ground. At the instant, it's 64 feet above the ground. So this sandbag is 64 feet above the ground, so that's the sandbag's initial height. Since the balloon is rising at 16 feet per second, that is the initial velocity of the sandbag. Oops, positive 16 feet per second. Because the sandbag was on the balloon, so it's rising at 16 feet per second. So that when it's released, it was still going that speed right at the instant it was released. How many seconds after its release will it hit the ground? So think about the position function. What would we want the position function to equal when the sandbag hits the ground? We should have it equal to 0. And then at what velocity will it hit the ground? Our position function will be negative 16 t squared, because we're dealing with feet, so we've got our negative 32 feet per second acceleration due to gravity. Negative 16 t squared plus our initial velocity, which is 16 t, plus our initial height. And so you can get that from starting with your negative 32 feet per second and integrating, doing the antiderivative. But we're going to do this so often, you may as well get used to it. S sub 0 is 64, that's going to go at the end. V sub 0 is 16, your initial velocity is going to go there. And negative 16 is going to be here. Now, if these were all in meters, we'd do negative 9.8. Negative 4.9, sorry, half of the acceleration due to gravity. Negative 4.9. T squared plus initial velocity, t plus initial height. So how many seconds after its release will it hit the ground? What we want to know is when will this hit the ground? So you can factor out a 16, negative 16. So we'll have 16 t squared minus t minus, I believe that's 4. And then that doesn't factor, so we'd have to use the quadratic formula. Oh, I thought I had spaces in there. Okay, so x equals negative b plus or minus the square root of b squared minus 4ac. Yeah, I know I'm a really good singer, aren't I? And you like my song? All over 2a. So we get 1 plus or minus the square root of 1 plus 16 over 2, which is 1 plus or minus the square root of 17 all over 2. And we want the positive value, so we're going to want, because time, this is time, not x equals, I should write the correct variable here. Time. We want the positive time value, so time equals 1 plus the square root of 17 over 2, which is about 2.562 seconds. So that's how long it will take for it to hit the ground. And then at what velocity will it hit the ground? So our velocity equation is the derivative of position. So the derivative of negative 16t squared. Yes, we're going to have to be going back and forth between antiderivative and derivative. We want the velocity at 2.562. Now I'm going to double check my calculation there. I should have used 4 decimal places if I'm going to do any further calculation. So 2.56155 is what I should be plugging in here. Since I'm doing further calculation, you should use at least 4 decimal places. So negative 32 times 2.56155 plus 16. Or it's even better if you just keep that value in your calculator and use your answer button. So I would do negative 32 times answer plus 16. So it's about negative 66. I should round to 3 decimal places, so that's truncated there, or negative 65.970, truncated or rounded. And the units on that would be feet per second. That's the velocity. Does it make sense that the velocity is negative? Because this sandbag is going down, its velocity will be negative. All right, there's your homework, page 257, 67 to 83 odd, and number 87. Enjoy!